Hello everyone, welcome to all in Pune University. My name is Dr. Manish Singh and I'm Associate Professor in Mechanical Engineering Department. This is a video lecture series on basic mechanical engineering and this is lecture number 4 of Unit 1. And in this lecture, I'm going to discuss with you molding sand, their properties and concept related to molding sand. Okay. So let's see, this is a table of content. In this, I'm going to cover lecture level outcome, molding sand and their types, ingredients of molding sand testing and their properties, and at the last, we will discuss some MCQs. So at the end of this lecture, students are able to understand how to define the different types of sand and their role in the casting, and they able to describe essential properties of the molding sand like permeability, strength, plasticity, refractiveness, etc. And students are able to explain standard tests used for evaluating the sand properties like moisture content, permeability test, compression test, etc. And they also analyze how ingredient properties affects the performance of molding sand, and obviously how to select the suitable molding sand for different casting process. So let's see one by one types of molding sand. So molding sand is a very essential part of the metal casting process because the entire mold cavity is made in the molding sand. Is that right? So the molding sand preparation, which I already discussed in the previous lectures, the molding sand preparation is one of the prime step in the metal casting, which influence the quality and quantity of the metal casting. Okay, so let's see first the types of molding sand. After that, we'll discuss the properties of molding sand and some ingredient of the molding sand, and later on discussion in this lecture. So first, we have a green sand, a sand which contains. If I talk about green sand, in this we have a silica sand. Silica sand, and its quantity is around 70 to 80%. Okay, 70 to 80% we use silica sand. And clay, if I talk about clay, then around 20 to 30%. This is ideal composition, but actually we consider less than this percentage. Okay. So this is clay percentage which we add in the molding sand, and similarly we add some amount of water, around 6 to 8% or 6 to 10% water we can add. And along with this, some binding agent may also used, around 4 to 5% of the total molding sand. So any sand which contain moisture and having composition like this, which I am writing here, is called as green sand. So sand in its natural or moisture state is called green sand. It is also called tempered sand, and it is a mixture of 20 to 30% of clay, and rest we have a molding sand, that is silica sand, and around 6 to 10% of water. Okay, and this is generally suitable for making small size casting, which is made up of ferrous and non-ferrous metals. Okay, so this is all about a green sand. Next, a dry sand. Dry sand means we have a similar green sand, but when we bake the green sand up to 100 degrees centigrade, then entire moisture get evaporated. So the sand which is free from the moisture contained or complete dried sand is called as dry sand. Is it right? And sand molds have greater strength, rigidity, and thermal stability as compared to as compared to green sand. And next, loam sand, ideally a sand which contains around 50% sand and 50% clay, then this is called as loam sand. But in actual practice, around 50% we use silica. Silica sand. Similarly, around 30 to 35%, 30% approximately, we use clay. And clay is actually, it acts as a binding agent. Is it right? It acts as a binding agent. And around 10 to 15% we add water. 10 to 15% we add water, and rest around 5% approximately we add some binding agent. So a sand which contains this composition is called as loam sand, and even loam sand is having very high strength as compared to a green sand or dry sand, and generally it is used for making large casting which is made up of gray caster. Is it right? So every sand has individual properties and individual applications. Next, a facing sand, a sand which is used to pour before pouring the molten metal. Is that right? So this is called facing sand. Let's suppose if you have the mold box, and here we have mold cavity. Here we have a mold cavity, and here we have obviously sand. Is it right? So inside this mold cavity, sometimes we sprinkle some sand, carbonous material with some dry sand, which prevents the bonding between the molten metal and the molding sand. Is it right? This is molten metal. So it prevents bonding between them, because during solidification the whole metal moves towards the center, and if metal which attached with the molding sand, if it doesn't break the bond, then obviously the sand wall may distorted, and some amount of sand particles may dislodge from the molding sand wall and enter into the mold cavity, molten metal, which produces sand erosion type defects. To prevent this, we always sprinkle some amount of carbonate material with dry silica sand. So this is called as facing sand. Is that right? This is called as a facing sand. And next one is a baking sand. Next one is a baking sand. So what is baking sand? Baking sand is nothing but it is a burnt reusable reconditioned sand. Burnt reusable reconditioned sand is called as baking sand, and actually during casting the sand which is nearby the molten metal get burned out, and it cannot be directly used for the further application. To make reusable, first we need to clean this sand and mix some moisture content along with some clay particle, and then this sand will become a reusable sand. So this reusable sand is called as baking sand, and generally baking sand is applied outside this zone. Is it right? Actually in this zone at inner side, generally here we use fresh sand. Is it right? Generally here we use fresh sand, fresh green sand, and outside this we use burnt sand, and this burnt sand is called as baking sand. This outside sand is called as baking sand. Is it right? So this is baking sand, and this is called as green sand. So simply by application of this, by use of this burnt sand, we reduce the consumption of fresh green sand. Therefore, our sand preparation cost may reduces, and hence our casting will be economical. Is it right? Next, parting sand, and you can see here the entire mold cavity we always make in a two half. One is cope, another one is drag. Is it right? And after solidification we need to separate them, and for the separation what I need to do, I just sprinkle some dry silica sand like this, dry silica sand or some carbonate material, and sea dust sand, these are used. And when we sprinkle this, then obviously it prevents the bonding between cope and drag. So this sand is called as parting sand. Is it right? This sand is called as parting sand. Next, core sand. Core sand is basically a sand which is used for making core, and in this, instead of using water, we use linseed oil. Obviously we have silica sand, and for bonding purpose we use linseed oil, or some other binders may also use. So this is called as a core sand, and it is used for making a core. And after making core, we just bake this core so that entire moisture contained in oil which is used as a binding get evaporated, and our core sand completely get dried. Is it right? So this is called as core sand. So now are you from this analysis you can understand what are the different types of sand and where this sand can be employed for the different purpose. Is it right? So once again you can see here, this is our fresh green sand. Is it right? Let's say I'm making green in color. So you can easily understand this. Okay. This is a green sand. And outside the green sand, we use burnt sand, which is represented by this black color. Okay. And a blue color sand, sorry, here we obviously here I am representing with blue, green color. This is the facing sand. Okay. So from this analysis, you can understand the application of different types of sands. Okay. Next, ingredients of molding sand. So many things are mixed in the molding sand. Generally 50 to 95% we use as silica sand. Is it right? And this sand may be coarse in nature or fine in nature. Coarse means if the size of the sand is bigger like this is called coarse sand. Okay, this is called as coarse sand or coarse grain. And if you use this types of sand, this is called fine sand. This is called as fine sand. So coarse sand and fine sand, neither we use coarse sand nor we use very fine sand. We use in between. Is it right? Why? You can see here coarse sand would have more white space between the grains, which increases the permeability. Is it right? Coarse sands have more gap. You can see if I arrange, let's say these are the sand, and if I arrange this sand like this, then this vacant space is called as void, and from this void the gases may easily escape. Is it right? So this escaping ability is called as permeability. So larger the sand particle size, larger will be the permeability. While as fine grained sand have lower permeability, however they have better surface finish. Is it right? Fine sand better surface finish, coarse sand better permeability. It means if you use very coarse sand, then you will get permeability, but the surface finish will be very poor. Similarly, if you use a very fine sand, then you will get the better surface finish, but the permeability will be very poor. So you need to compromise both permeability as well as surface finish. That's why we use optimum size of sand, so that we will get the better surface finish as well as better permeability. Is it right? Next, generally silica sand SiO2 low melting temperature alloy sand is used for non-ferrous alloys. It is generally employed for non-ferrous alloys. And zirconium sand is generally, its melting temperature is very high, so it is used for casting of steel, or you can say ferrous alloy. But sometimes cast iron may also casted with the help of a silica sand. Okay. Next, a very important point with reference to sand is the shape of the sand grains may rounded, angular, or subangular. Angular means a sand particles like this, or sand particles may be like this, and sand particles may be like this. Okay. So this is rounded, this is angular, and this is subangular type. Is it right? And it depends upon the geological position. Is it right? Means from which location you extract the sand, means from which river you extract the sand. So this is called as a shape of the sand, and even angular sand produces better surface finish than the other shapes. Next, clay. This is also a very important ingredient of the molding sand. Molding sand may may contain around 2 to 50%. Is that right? Around generally in green sand we use 10 to 15%, 10 to 20% clay, and in loam sand generally we use 30% approximately. Is that right? Ideally we can use 50%, but actually we use around 30 to 35%. So this is called clay. And what is clay? Actually, this is a mud. Okay, this is a simply a soil. Okay, and when you add some water in the clay, then it get activated and form a gelling action. Means it makes like a keychad. Is it right? Suppose this is a sand, and in this when we add some water, then it get activated and they form a like a gel. Is it right? And this gel has very good binding ability. So if you employ this gel between two sand particles, let's say this is a sand particle, and in between the sand particles, if you apply this gel, then a proper bonding takes place between them, because sand particles, which is obviously they don't have bonding ability, so they cannot make a bond between them without using some any binding agent. So clay act as a binding agent. Is it right? And water, yes, without water clay cannot work properly. Why? Because it is also not having binding ability. But when we add water in the clay, then it gets activated and form a gel, and this gelling action is actually suitable for the binding purpose of the molding sand. And generally we add around 1.5 to 8% of water. Generally we use 6 to 8% for silica sand, 6 to 8% for green sand. Is it right? And around 10 to 15% we use in loam sand. Why? Because larger the quantity of clay, larger the water requirement. Yes or no? That's why we select percentage like this. Next is some special additives we also use to improve the hardness strength of the molding sand. Like we use cereals. It is fine ground corn flour. It may be used in a molding sand for increasing green or dry strength, and we also increase collapsibility of the molding sand. Okay, and it may be added around 2%. Ground pitch. It is a product of coke making. Is it right? Coke making, which is distilled from a soft coal, correct, and it is used an amount of 3% to improve hot strength. Hot strength means a sand should have a enough hot strength to retain their temperature at elevated temperature. Is it right? And asphalt may also use, and it is a byproduct of distillation of petroleum, and its purpose is like a pitch. Is it right? It also increases the hardness of the strength of the molding sand, correct? Next, sea coal. Sea coal is fine ground soft coal used in the molding sand. Is it right? And it is a carbonious material, and generally it is used for getting better surface finish and improving collapsibility of the molding sand. And even it is used to improve the detachability of the pattern from the molding sand, so that easily pattern can be withdrawn from the molding sand. Is it right? And graphite, of course, synthetic or natural graphite may be used in the percentage of 0.2 to 0.2%, and its purpose is to improve moldability of a sand and surface finish of the casting. Is it right? Means, see, when you ram, let's suppose if you have, this is a pattern and this is a mold box, and when you fill the molding sand, and after that obviously we need to do ramming action, then the molding sand have enough flowability so that when we apply ramming force, then it can flow easily around the corner of the mold box. Is it right? So that it can fill the entire section of the mold cavity. Is it right? So this is the purpose of graphite. Next, sawdust and good floor. Again, it's a good floor. Good floor, around 1.5% we add in the molding sand. Is it right? And it also increases the green strength of the molding sand, and it reduces the expansion defects with improving flowability of the molding sand. And by the addition of sawdust, sawdust means burada. This is a byproduct of the wood cutting. Is it right? So if you add this sawdust or wood floor in the molding sand, that it enhances the collapsibility. Is it right? It enhances the collapsibility of the molding sand. Is it right? Collapsibility of the molding sand, correct? And obviously, in a facing sand, we use this sawdust or a wood floor, okay? And silica floor, pulverized silica finer than 200 mesh is called silica floor, and it is used in an amount of 35% for the purpose of increasing hot strength of the sand, and it also increases the density of the sand to resisting metal penetration. Is it right? See, if you have this is a mold box, okay? This is a mold box, and this is a mold cavity. The mold cavity, and obviously here we have a molding sand. And if you have, see, if you have more gap between the sand particle, then the metal can, if you fill this molten metal, then metal can easily penetrate in this gap. And if it can penetrate in between the sand particle gap, then obviously it produces irregular surface on the casting surface like this. Is it right? So further, for getting desired surface finish, you need to remove this extra material. To enhance this, we add this silica floor. It is a pulverized silica with a very fine particle sand, and if you add in the sand, then obviously this gap will reduces, and hence it prevents the penetration of the molten metal inside the in between the molding sand particle. Is that right? So this is also called as hardness of the molding sand. So basically the silica floor may increase the hardness of the molding sand. Okay. Next, you can see the properties of the molding sand. So first property is refractiveness. What do you mean by refractiveness? It is the ability of a molding sand to withstand high temperature, correct, against the liquid metal. So this is called as refractiveness, and every molding sand should have this refractiveness property. Is that right? Otherwise, if refractiveness of the molding sand is less, and if you pour the molten metal, then the sand particle itself may fuse and mix with the metal and produces some other structure which produces a poor surface finish, and even it produces difficulty in the machining. Next step, permeability of the molding sand. Permeability means gas evolving. I already told you, let's suppose this is the molding sand and it is bounded like this. So this gap is basically, this gap is called as a void, and from this void, suppose you can see here, this is a mold box and this is a mold cavity. Is that right? And when you pour the molten metal, then because of this molten metal, the moisture which is nearby the, which is in contact with the molten metal, get evaporated, and if it is trapped inside it, then it will produce a gas hole type defects. So enough space must be provided so that these gases may escape from the mold box. Is it right? So this escaping of escaping of gases from the mold cavity is called as permeability. So simply you can say breathing capacity of the molding sand, or it is also called as a gas evolving capacity of the molding sand is called as a permeability. Is that right? And permeability mainly depends upon the grain size, grain shape, moisture and clay. Is it right? Grain size, obviously I already told you, if you have a fine grain, then the permeability will be lower, and if you have coarse grains, then in case permeability will be higher. Is it right? And grain size, obviously if you have a perfect spherical shape like this, then you will get better permeability, rather than if you have a angular type grains like this, then you will get a lower permeability. Is it right? Moisture content, obviously if you have moisture, if I plot a graph between moisture versus a permeability, so initially permeability will increases, and after that it will be decreases, and the ideal range of this moisture content ability addition is 6 to 8%. Is it right? If you add around 6 to 8%, then you will get better permeability, and if you add more than this, then you will get poor permeability. Even less than this, then again you will get the lower permeability. And of course clay, it depends upon the clay. And permeability is represented by this number, that is Pn is equal to Vh over Pat, that is V is a volume of 2000 cc of air that can be moved from the standard specimen, and h is the height of the specimen, which is 2 inch, that is 5.08, and p is the pressure, a is the area of cross section of this standard specimen, and t is the time taken to pass this 2000 cc of air. So basically we have an instrument like this. This is a permeability tester. In actually in this we have a two container. One container, outer container, you can see this is a hollow container, and inside this another hollow container whose top end is fixed. Is it right? You can see here. So inside, when you put your sample somewhere here, and it is connected with a pipe. So obviously when you move this this portion of the container upside, then the air gets filled, and of course here we also have a water. Is it right? Here we have a water, but we provide a provision so that only air can move. So when initially, and one more thing, in this container we have a mark which shows the amount of volume of air that can be accommodated. Is it right? So at the top here we have 2000 cc. Is it right? So you just lift this internal container up to 2000 cc volume, and after that you just open this valve and start your stopwatch so that you can measure the time, how much time required to pass to move this container inside it. Is it right? So actually when it is moving inside it, then air can moving through the standard specimen. Is it right? And of course when this container is moving down, then the slight pressure it also increases, and that pressure is measured with the help of this manometer. Okay, so you just need to measure time as well as the pressure, and once you measure, then you just put these values in this standard formula, then you will get the permeability number. Next, this is a mold testing grain fineness number testing sieve shaker testing machine, and in this we have several sieves which are different mesh size, and actually if you see its top view, then we have sieves like this. Actually steel wires, with the help of these steel wires we make a sieve, and this is called as mesh size, and with a varying mesh size we put the sieves. Obviously a coarse mesh placed at the top, and fine and finer than fine meshes are placing at the downward side, and at the last we have a pan. And now a fixed quantity like 100 gram complete dry sand we just put on the upper part of the sieve, and when you start this machine, then automatic sieving action takes place in this system, and because of this automatic sieving action, the according to the mesh size the sand particles get settled down, and after settled down we just measure the quantity of those sands, and after that you just put the weight. You can see put the weight of molding sand in each sieves like this. Is it right? And with reference to each sieve number we have a multiplying factor, then you just multiply this multiplying factor with the retained sand in each sieve, and after multiplying you will get this result. And even you can also represent in the percentage form, but it is not necessary, so need not to represent this. So only you just write down the quantities of molding sand in each sieves, then you just multiply with this number and put in this table. Okay, and after that we have a formula, that is summation of MIFI over summation of FI. Is it right? Correct. So from this ratio you will get the grain fineness number. So this is called as a grain fineness test. Next properties of the next property, that is strength. Strength is also a very important property of the molding sand, and especially when I talk about green strength. So green strength is nothing but it is a strength of the molding sand which retain their shape and size while withdrawal of the pattern. So this is called as green strength, and it is around 30 to 160 kilopascal. Is it right? And every sand must have enough green strength so that while withdrawal we can easily withdraw the pattern without sand erosion or without collapse of the molding sand. Similarly, dry strength, obviously when you pour the molten metal, then when the molding sand come in contact with the molten metal, the moisture get evaporated and it will become a dry state. And during flow of the molten metal further, let's suppose if you see here, this is a runner, sorry, pouring cup and sprue, then this is runner and this is mold cavity. So when you pour the molten metal like this, then obviously molten metal rubs this surface. Is that right? So when it is come in contact with the molding sand, the entire moisture get evaporated. Then the sand nearby this molten metal get completely dried. And when this molten metal is flowing, then the molding sand should have enough strength, dry strength, to retain their position and prevent the sand erosion while flowing of the molten metal. Is that right? So this is called as dry strength and hot strength. And obviously when you fill the molten metal inside the molding cavity, is it right? Then obviously during solidification, this metal gets shrinks towards the center. Then the molding sand have enough hot strength because its temperature is very high. So enough hot strength to retain their sand particles during shrinking of the molten metal. Is it right? So this is called as hot strength. So all strength like a green strength, dry strength and hot strength, it is essential for every sand, so that after that if they have a adequate property, then we will get the sound quality casting. Is it right? And next, mold hardness. After making a mold cavity, you have a mold box like this. Is it right? We have a mold box like this. This is half portion cope and half portion is drag, and it is completely filled with sand. Okay. So we have a mold hardness tester like this, in which we have a dial gauge. This is a plunger, and this plunger is connected to this spring, and here we have indicator. Okay. So now when you put this hardness tester, over this molding sand, when you put this hardness tester over the molding sand, then this plunger can plunge inside the molding sand, and accordingly this dial indicator may move here and move in this path. Then you will get the reading. Is it right? So the molding sand should have adequate hardness so that it can prevent the penetration of the molten metal between the molding sand. Is it right? And it is tested by this mold hardness tester. Next, properties of the next thermal stability. The molding sand should have adequate thermal stability so that during pouring the sand particle can retain their shape and size. It never be expand or contract. Is it right? Or buckle. Flowability. The molding sand should have enough flowability so that while ramming, the sand particles can easily move here and there, so that it can fill the indicate location of the we can say mold box. Okay. So this is called flowability. Next, collapsibility. What do you mean by collapsibility? Collapsibility tells us the detachability of the molding sand, means how the molding sand and molten metal get easily detached to each other. This ability is called as collapsibility. And what is cohesiveness? Cohesiveness, it tells us the bonding between dissimilar particles, means bonding between sand and the we can say sand and the binding agent. Is it right? So this is called cohesiveness. And next, the types of method of molding. So obviously we have floor molding. Floor molding means you just put your pattern surface plate on the floor and do the molding practice. Then this is called floor molding. And what is pit molding? If your size of the pattern, size of the casting is very big, then we generally dig a hole, bigger size hole in the floor surface, and inside this we make a drag portion. Is it right? And cope always made above the surface. So this is called a pit. So that's why this is called pit molding process. And generally this pit molding process is used for making a very large size casting. Is it right? And next one is machine molding. Then obviously there are three types. That is jolting. Jolting means you just fill the molding sand around the pattern, and you just after that you just lift the pattern and throw it by a height of 5 centimeter gap. Then because of this lifting and throwing, the entire sand particles get properly rammed and settled down. Okay. And next one is squeezing. Obviously after putting the pattern and the filling the molding sand, you just with the help of this ram, you just press, then the molding set get rammed uniformly. So this is called squeezing. And this is the sand slinging. You can see in sand slinging, actually we have a sand slinger in which we have multiple buckets which collect the sand and throw at a very high speed. So along with filling, ramming action may also takes place. So this is called as sand slinging, and all these processes are machine molding methods. And this is a muller. and its purpose is you just fill all the ingredient like silica, sand, clay, moisture, additives, and after that when you run this machine, then this roller rotates about this, and this system can also rotate about this axis. That revolutionary and rotatory action both takes place simultaneously, so entire sand gets mixed properly. So this is called as a sand mixing machine. Okay, so this is all about sand, their types, properties, and molding methods. Okay, so now the time is MCQ questions. So let's see one by one. So what is the primary purpose of manufacturing process? So to create a final product from the raw material, to refine raw material, to reduce the weight, to mix the different metals. The primary purpose of manufacturing process to create a final product from the raw material. Okay. What is the basic definition of metal casting? The process of heating metal until it becomes liquid and pouring into the, this is called as a metal casting process. Okay. So rest of the question you can just try. So I think this is enough for this lecture. So now I'm going to end this session. Thank you for watching and good day to all of you guys. Let's meet in the next class.